Welcome to this little mini session on grade 5 math. We're going to be looking at how we can connect multiplication, area, and divisibility rules. So if you're listening during this little session and you have a question, please feel free to ask it. And if you're watching the recording, feel free to just send us an email. Oops. So you'll be able to find all of these resources on the Chinook's Edge New Curriculum website. And when you go down to the grade 5 section, the long range planning documents, you'll find this in both the number planning document and the measurement planning document, number under learner outcome 3 and measurement under learner outcome 1. You'll just scroll down until you see learning, and then you'll see CESD's grade 5 connecting multiplication, divisibility, and area. So when I started this planning for this, I asked myself what outcomes and what costs really fit together with what my intention was for this process. So I went through and I looked at outcomes and I looked at costs, and I was very deliberate about which ones I chose. I was looking for really strong connections, not the soft ones that I always end up doing, but very deliberate ones. So in the handout that in the long range planning document, when you click on this file, you'll see the pieces that I picked. Number, in this case, grade 5, number 3, students determine divisibility of natural numbers. And then I bolded all of the costs that I felt matched, which obviously was all of them as it applied to this particular learner outcome. Then I asked myself, where else does it fit? Because the more often that we connect outcomes, the bigger bang for our buck we get. We're hitting multiple outcomes at once. More outcomes we help students connect to, the better their understanding and connections will be, and the longer that they will retain it for. So when I looked at measurement and I was thinking about area, there's really only skills and procedures number 7 that was specifically addressed here, which was the area of a rectangle. But we do start to flow into some of the other ones as well, but they weren't just quite as strong. And I'm focusing on using 1-inch tiles for a lot of this, whereas most of this is the metric system. But you'll still be able to play with that conversation around area as well. Students should have prior experience creating and understanding multiplication as arrays. And if you take a look in the grade 4 number strand, you'll find a file called Connecting Multiplication, Prime and Composite Numbers in Area. So even if your kiddos haven't done it, or even if they have done it, you can go ahead and start with those pieces in order to kind of connect back to what they should have done in grade 4. And it's a great entry point for kiddos, especially if they're struggling with multiplication, prime and composite numbers in area. For these activities, you can use 1-inch square tiles. I've got the integer tiles that are the red and black ones. And then we've also got some solid color tiles. And again, they're 1 inch, which is really nice for the grade 4 piece, and the grade 3 if you're looking at measurement for imperial. The other thing I forgot to put a picture of in here is we'll be using base 10 blocks for part of the questions as well. This is a nice extension. This is Joe Bowler's number visual activity. So I would suggest including that as an opportunity to make connections. And then we've got Dan Finkel's Prime Climb. So those are really nice ones as well for more extensions, for more connections. And then I've linked the divisibility by 2 slideshow and the divisibility by 3 slideshow, which we'll be walking through. A bottoms up hundreds chart. I like bottoms up rather than top down, because as the numbers go up, place value increases and things like that. So it's a lot more logical. Blue and red pencil crayons. And then I'm not going to get into this today, but I created this little document in order for you to put your cusps together if you are doing some formative assessment to keep track. All right, so the lessons are going to kind of run like this. We're going to explore divisibility by 2, and I've linked the slideshow there. It's also linked in the handout. We're not going to go through all of that today because it kind of just repeats itself. Divisibility by 5 is the exact same thing as divisibility by 2 for a process. So you don't have to go through the slideshow again. You can just kind of talk to kiddos about using what they know about that process for divisibility by 2 and applying it to 5. Then we're going to actually dig into divisibility by 3 today during this video. And then you can explore with students divisibility by other natural numbers between 1 and 10. Students only in grade 5 have to know 2, 3, and 5, but the other ones are nice to explore and look for patterns. They just don't have to have the rules memorized. Then you can also talk about the idea that you can't divide by 0 as well. So I'm going to switch my screen to the divisibility by 2 slideshow. For this one, you don't need all of your supplies, just the square tiles, hundreds charts, the pencil crayon and Joe Bowler's number visual, and as well as some of the prime climb images as well. So what I would do is I just give students those square tiles and I'd say, can you build a unique array for the number 6 with a dimension or factor of 2? And you can see here, this is why it's so important that they have done that pre-work from grade 4. If they're not sure what I mean by a unique array or what I mean by factor of 2, those are grade 4 ideas, but you may have to explore that. So what I mean by a unique array for the number 6 is you might have 2 arrays that look the same. So here's an example. You might have built this array, or you might have built that array 90 degrees flipped. And you might be wondering, well, are they the same? Well, they're the same area. They have, when I look, I can see 2 3s, and when I look, I can see 3 2s in both of them. They're not exactly the same because they have different orientations. But if all I do is turn my head and change my perspective, then I can see the commutative property for multiplication. 2 times 3 has the same value as 3 times 2. They're not identical arrays when they're turned, but we will kind of put them into the same lump and call them one unique array, whether it looks like this one or if it's turned on its sideways, on its side, and you see the other array. So for students, one or the other would be considered one unique array. So yes, we can build a unique array for the number 6 with a factor of 2. Can you see the factor of 2? Yes, because it has a dimension of 2 there. And the area is 6. Now I might say that that's a 3 by 2 array or 2 by 3 array, depending on which way that I built it, depending on your context. It really doesn't matter which way you go. There's only specific situations where it's going to be important for them to know that, and that's not in grade 5. So today, because we are looking at divisibility of 2, we are going to use one that's bolded. We're going to use 3 multiplied by 2. We're going to refer to that as 3 2s. I could have said 2 3s, but then I'm not drawing my attention to the divisibility of 2. Instead, I'd be looking at the divisibility of 3 there. So we'll look at 3 2s as the reference here. And I've already answered the question, what is the area of 6? Then we just move on. Can you build a unique array for the number 7 with a dimension of 2? So we're starting with really easy numbers. These are all multiplication facts that students would have learned in grade 3 and grade 4, and we're just connecting to that and building upon it. So no, we can't do that. So what's the best you can do? What's the closest array that you can build with a factor of 2? Well, we can build 3 2s, and we have 1 left over. What's the area? Well, my area is 7. Can I build a unique array with an area of 8? And I'm just going to keep repeating those same questions. Can I build it with 9? What's the best you can do? 9 is 4 2s and 1. So we're starting to play with decomposing numbers in order to make multiplication a little bit easier. After I've done all that, then I can put the 4 that we just looked at, put them on the board, and we can start looking for patterns there. What do you notice? What do you recognize? What relationships do you see? And students are probably going to notice, well, it's every second one. I wonder if it's always every second one. So then we can pull out that numbers, the bottomed up hundreds chart, and get students to figure it out for all of the numbers 1 to 20. Which ones were you able to build as an array with a factor of 2, with a side dimension of 2? And we're going to circle those in red. So there's the numbers 1 to 20. What patterns do we see? And what relationships do we see? And we can start to have those conversations. Then I can ask kiddos to extend the pattern, because mathematics is a pattern finding subject. It is not an answer finding subject. So how might I use what I just looked at in order to determine if 32 will work? Test your theory, so then they can build it. How might that help you determine if 43 will work? And test your theory. And then they can play with numbers and just start to formulate the idea of divisibility by 2. After they've done that for a few numbers and they've got some experience, then I can help them extend that pattern. So can I use what I already know about 6, about 3 2s, to figure out if 60 will work without using the rule? Engage students in that conversation. So what do I know about 60 as it relates to 6? Well, I know that 60 is 10 6s. So I can write that as a multiplication statement. I can write that as words. And then I can say, yeah, 60 is divisible by 2 because 60 is 10 6s, because 6 is divisible by 2. I could draw it and I can take those 10 6s and outline them so they're one long array as well. And I can still see that it has a dimension of 2. Then I can take that and ask them to apply it to 600. Again, 600 is 100 6s. And ask them to apply that to 6,000 and 60,000 and have that conversation about why I'm able to do that with the number 6 and relate it to all of the ones that are connected to 6 as well. Then we can talk about creating a starter rule. I often use the phrase. Let's start that rule off. It may change as we learn about more complex numbers, or it might not change. What's that rule for determining if a number is divisible by 2? And I want them to be thinking about, because I can create an array with the factor of 2 of that number. And then I can start talking about how that only ever happens with even numbers, never odd numbers. Then they can go and apply that to their hundreds chart. Now, I'm not going to go into this aspect. These are the prime climb factors, the prime climb number trees. We have prime climb. I have a copy of prime climb, the game. If anybody wants to borrow it, you can try that out. But it's a great way to talk about factors of numbers. This is less about area, but more about factors. And then you can explore divisibility in here as well. But I don't want to spend any time here, because I really want to get to the divisibility of 3. So I'm really excited with what I'm going to share with you around divisibility of 3. When I grew up, I learned the rules for divisibility of 3. I learned that all you had to do was add up the digits. I had no idea why that worked. I just did it. So then a couple days ago, I actually looked up what the math was behind it. And I'm like, okay, the math sort of makes sense. But what's the concrete that I can do to start with that? What's the hands-on piece? Because as we know, kiddos are always going to build better understanding, build better visuals, and make better connections if you start with the concrete before you move to the pictorial, before you represent all of that abstractly. So I figured out what that looked like today, and I'm really excited to share that with you. So we can do the exact same process that we did with the divisibility of 2. We can ask students to build a unique array for the number 3 with number 6 with a dimension or a factor of 3. And we can walk through that exact same process. So I'm going to connect back to what those kiddos have already done previously within this class, previously within previous grades, because those connections are super important. So this doesn't look any different than what we have seen before. We can engage in those conversations there. Repeat for the rest of the numbers. Circle those numbers in blue this time. What patterns do you see? Extend it. And then you'll notice that this looks very similar. All right. So now I'm going to take it to this piece before I move on to the new learning. But what I want you to think about is 1 times 3 divisible by 3? Is 2 3s divisible by 3? Is 3 3s divisible by 3? And how do you know? So a student might say, well, I've got a dimension of 3, and which makes it divisible by 3. That's really important. How about 3 1s or 3 2s or 3 3s? How do you know those are divisible by 3? And again, students can engage in that conversation. Well, if it's 3 1s, I've got an array of 3 by 1, which means it has a dimension of 3, or 3 by 2 is a dimension of 3. Then I can talk about 1 4. Well, No, that's 1 by 4 or 2 by 4 or 3 fours. Oh, that one does because it has a dimension of 3 in there. Then I can go to 1 6. Well, there's no 1, there's no 3 in there. Sorry, there's no 3 in either spots, but 6 is really 3 by 2. So I can start playing with the idea. I could represent 1 6, turn it and just slide it, and I can see 3 2s in there or 2 3s in there. So I'm going to have students check this out, explore it, see if they can figure out which ones do, which ones don't, just to start building relationships. And then they can start by creating a starting hypothesis regarding numbers divisible by 3. So if it has a factor of 3, it'll be divisible by 3. All right, now this is the part I'm really excited about. So I've got one base 10 block on the screen. Is 1 divisible by 3? No. What about 2? No. 3 is, though. Awesome. 4, no. 5, no. 6, yes. 7, no. 8, no. 9, no. Yes. All right. 10, no. So now I have a 10 of a base 10 block. So what I'd like you to do is take a moment to think, what is the biggest chunk of 10 that is divisible by 3? So take a moment to think about that. When I'm looking at 10, what's the biggest number within 10 that is divisible by 3? We just went through all the numbers 1 to 10. You probably said, well, 9 is. 3, 6, and 9 are, but 9 is the biggest chunk that is divisible by 3. So I'm going to take that base 10, the 10, and I'm going to kind of split that 9 out. The 9 is divisible by 3, but the 1 isn't. All right, so is 11 divisible by 3? Well, I know that the 9 orange are, and then I've got 1 left over from the 10, and I've got 1 more. So I've got 2 left over. 2 is not divisible by 10. 11 is not divisible by 3. My apologies. So let's take a look at the next number. Is 12 divisible by 3? So you can see in your 10, you've got the 9 all chunked. We know that's divisible by 3. We've got 1 left over from the 10, and we've got 2 from the 2 that make 12. How many are there all together? And why is 12 divisible by 3? Well, I've got 1 left over from the 10 and 2 from the ones place. So I've got 3 left over, and 3 is divisible by 3. What about 20? Take a moment to take a look at that one. So when I take a look, how many are left over from the 10s that weren't divisible by 3? Well, I've got 2 left over. And that's all I've got left over. 2 is not divisible by 3. All right, is 21 divisible by 3? So when you put it in this format, it's a lot easier to see what's divisible and what's not. So I have 2 left over from the 10s. So I've got 2 left over from the 20. And I've got 1 left over from the 1s. I've got 3 left over altogether I haven't accounted for, and 3 is divisible by 3. Let's look at the number 40. How many are left over from the 10s? Well, there's 4 left over from the 10s. And there's nothing left over from the 1s because there weren't any. But 4 is not divisible by 3. What about 41? Well, I've got 4 left over from the 40, and I've got 1 left over from the 1s. So altogether, I've got 5. 5 is not divisible by 3. What about 42? I've got 4 left from the 40, 2 left from the 1. So altogether, I have 6 left over, and I can make that's divisible by 3. So 42 is divisible by 3. So now what I want you to do, because we've been, with kiddos, we'd be building that using base 10 blocks. I've been doing it pictorially, but now I'm going to ask you to visualize it. I want you to visualize 56 built with base 10 blocks. Look at your 5 10s and look at your 6 1s. And I want you to just for a moment focus on your 10s. How many leftovers do you have from the 10s that are not divisible? So you should have said you have 5 left over from the 10s. And how many 1s do you have? Well, you have 6 1s. So you've got 5 left over from the 10s. You've got 6 left over from the 1s. So you've got 11. Is 56 divisible by 3? No, because 11 is not divisible by 3. And there's my proof. This time I'd like you to picture 84. How many are left over from the 10s, from the 80? How many are left over from the 1s, from the 4? So you've got 8 from the 10s, 4 from the 1s. So you've got 12, and that I can show is divisible by 3. So 84 is divisible by 3. And there's a visual proof of that. So then I would spend more time in 2 digits with kiddos. I'd get them to pick some numbers and just use that idea of building it, finding your 9s in there, finding what's left over from the 10s, finding what's left over from the 1s, and playing with that before you move on to hundreds. When we're ready, then we'll move on to 100. So consider 100, and I know it's not square, it just stretched a little bit, but consider the 100. What do you know as it relates to what we've just talked about? So I can see I've got 10 10s in there, and each of the 10s, it has 1 left over. So I have 10 left over from the 100. So I know this 10 makes it a little bit interesting for when I'm figuring out divisibility. So is 100 divisible by 3? Well, if I've got 10 left over, 10 is not divisible by 3. So 100 is not divisible by 3. What about 120? So how many do I have left over from the 10s and the 100? So I've got a 10 left over from the 100. I've got 2 left over from the 20, and I don't have any 1. So I've got 12 leftover pieces here. 12 is divisible by 3. So 120 is divisible by 3. Let's just extend that one more, 136. So my 100 has 10 left over, my 30 has 3 left over, and my 1s has 6 left over. So I've got 10 and 3 and 6. That is 19. 19 is not divisible by 3. Now you might be thinking, I'm not sure if I know if 19 is divisible by 3. So what are the opportunities for me to use what I know about this 10 to figure out, to make that a little bit easier to figure out? Well, 10 is just 9 with 1 that doesn't divide. So this 10 is kind of like another 10 over here. I don't know if you can see my mouse or not, but I can shift that back over to the 10s place in my head and treat it as another 10. So what I'd like you to do in your head, because we're going to take it from concrete to visualization, is imagine 237. Look at your hundreds. How many do you have left over? Oops. You've got 20 left over. Imagine your 10s. You've got 3 left over. And imagine your 1s. You've got 7 left over. So I've got 20 and 3 and 7. But that 20, if I show the picture, is really 2 10s left over there. And I know that 2 10s is really 2 left over. So if Johnny says to me that when I look at the number 237, I could really just treat that as 2 left over and 3 left over and 7 left over and have 2 plus 3 plus 7. Do you agree? Do you disagree? Why? So it's a good it's a nice lead in, and I went through this very quickly just due to time, but it's a nice lead into where does the rule come from? Why can we just add the digits in a number in order to find out if it's divisible by 3 or not? So it's that kind of back process for students to see. Much slower, a lot more practice with numbers, but students can absolutely figure that out. So then putting it in the student's hand, how might you use this to help determine the divisibility of a different 3-digit number? Choose a number you know will work and prove it. Choose a number you know will not work and prove it. Maybe they might just choose a number because they're not sure, a tricky number, and prove if it is or isn't using that process there. And then can they take that and apply it to a 4-digit number? So I might just give students 1,000 cube and say, here you go, here's a visualization of 1,000. What do you know about this? And how can you use that to help you figure out divisibility of a 4-digit number as it applies? So it's a nice extension within grade level. So it's an opportunity to demonstrate excelling understanding. And I'm not going to go on to the rest of these because I'm out of time, but there are, I think it's so important in mathematics that we always, always look for the concrete representation of why mathematics works, why the rules work, and then lead them to being able to use that in an abstract context. Because if we don't start with the concrete, if we don't explain to students or help students develop that understanding of what's actually going on in the background, they'll memorize a rule for a test, and then that rule is going to get thrown out when they learn different rules. And it's why we see students who are struggling because they've tried to memorize so many rules, and there's only so much space in their brain for random rules with no context. So I'm hoping that you found this helpful. And I look forward to chatting with you guys about this some more in the future. Are there any questions? Well, if there are no questions, I'm going to stop the recording, but feel free to email me if in the future you have anything that kind of pops out as something you want to ask. Feel free to email me or give me a shout. So thanks for joining.